Good morning, everyone. Welcome again to our event. Today is the last day of the workshop on control theory in partial differential equation. Thank you, everyone, for your presence. We really appreciate to have here in this workshop. So the first lecture in this morning section will be given by the Professor Jaime Angulo. It's a pleasure for me to introduce him. Jaime is a full professor of USP Sao Paulo University. He works in nonlinear G-specific equation. He has many papers. He also has formed several students, such as masters and PhD students. Thank you very much, Jaime, for having accepted our invitation. So in this opportunity, Jaime will be talking about the unstable kink profiles for the size coordinate equation on Jobson junction. Thank you, Jaime.
Okay, Carlos, thank you very much by the introduction. And I would like to thank both the scientific and the organized committee by the invitation to participate in very nice workshop. Okay, the results to be presented here are in collaborations, okay, with Ramon Plaza from the UNAM in Ciudad de Mexico. Let me talk about the goal of this talk, okay? The first one is that is to provide, okay, new approaches in the mathematical studies of nonlinear dispersive equations on metric graph, okay? Here, I will establish a linear instability criterion for soliton profiles on general metric graph. In particular, I will study the instability properties of kink soliton profiles for the sine-Gordon model on Y junction, so-called Josephson junctions metric graph. Okay? Okay, let me introduce some frameworks about the metric graph. A metric graph here will be a structure represented by finite collections of semi-infinity H parameterized by the positive or the negative half-lines attached on their origins. Nu equals 0 is called the vertex of the graph. Okay, sometimes in the literature, G is sometimes called a star-shaped metric graph. Here I put a very innocent graph with 6H, okay? In the following one, we have a Y junction, okay, which is a metric graph with 3H, one negative half line and two positive half lines, okay? These frameworks will be the main graph which we will work here related with the sine-Gordon equation. Okay. In general, a metric graph can be associated with a set of indices, okay, A minus and A plus, which are finite collections of semi-infinity H parameterized by the negative or the positive half lines. Sometimes here I will use the notation Li, okay, and every element of the graph G, I will use this vectorial notation where every component UE is defined in the corresponding H, LE on the graph, okay? Here I show I call this a representation of a profile on a Y graph on a Y junctions. Here we can see that it's possible to have discontinuous profiles for elements, okay, on a metric star graph, and this is an obvious case where you have a discontinued situations in the vertex. Okay, now it's natural here we can introduce the L2, the Hilbert space L2 as this direct sum, okay, of copies of L2 on every half lines, positive or negative. We define the norm and this L2, okay, in this natural way. So we can define the inner product, okay, on this L2 space by using the natural or the usual inner product in L2. More exactly, for every two elements on the graph, we define the inner product in this specific form, or if you open this sum, we obtain exactly this expression. Okay. Okay. Also, we can define the Sobolev space Hn for n positive integer, which is defined again as a sum, is a direct sum of any copies of the classical Sobolev space on every half lines, okay? And we obtain immediately this definition for the norm. Here it's very important to see that in this definition, we're not assuming any condition about the values of the function in the joint point v equals 0, or in other words, in the vertex. Okay, now wave dynamic and brushed structures in general is motivated by the demands of reliable mathematical models for the different phenomena in brushed systems, which in meso or nano scales resemble a thin neighborhood of a graph. Here, I have a specific example of this situation. Here we obtain a very simple artery network where you can, this artery is in fact a thin neighborhood of a Y junction. Okay? Okay. Now, from a mathematical viewpoint, the nature of the PDE model on a graph is equivalent to a system of PDEs defined on every edge of the graph. The main point here is the coupling of these systems is given exclusively through the boundary conditions in the vertex or the other vertices, okay, which appear in the graph. This condition sometimes is known in the literature as the topology of the graph. Okay, now many models has been used to describe many physical situations. Okay, by example, in optics, in neuroscience, in nanotechnology, and the blood pressures, waves, and large arteries, and in Y Josephson junction network, which appear in superconductors. Okay. Here I put, or I give three references which can give you a very nice vision about the theory, okay, of and applications of the metric graph in technology, okay, in general. Okay. Now, in the past years, the study of linear models in general has made good progress, and there is a broad literature about this subject. In this point emerge the definitions of the quantum graph. Quantum graph is a metric graph equipped with a differential operator H, so-called Hamiltonian, accompanied by appropriate vertex conditions. Okay? With that information, we can consider then a specific linear evolution equation. Okay? Now I will give an example of a quantum graph on a Y junction. In this case, I will consider the linear Schrödinger equation, okay, here. okay, where the Laplacian defined on a Y junction is defined via this action. In other words, we obtain that the second derivative is applied on every edge of the graph, in this case on a Y junction. Okay. In other words, the systems of PDEs associated to this general equation is exactly the linear Schrodinger equation, the very classical linear Schrodinger equation on every edge. Okay. Now we have two vertex conditions associated to the Laplacian operator, which appear continually in application. Okay, the first one is the delta iteration, which is this explicit domain with element of H2. Okay, where they are continuous in zero, and we have these specific Kirchhoff conditions in zero. Okay. The other iteration is the delta prime condition or the delta prime domain, where we have the continuity of the derivative. Okay, and in this case we have this Kirchhoff condition associated to the functions. Okay, with these two domains, we have that our Y junction becomes a quantum graph. Okay. Okay. Well, now the introduction of some nonlinearities in an evolution model, the network provides a very nice fields where we can looking for very interesting nonlinear problems about the well-posedness, blowout dynamic, or also about the soliton propagations. Okay, in the last years, okay, two nonlinear models have been working. The first one is the nonlinear Schrodinger equations on a star graph. Here, the expression of star graph is a metrical graph, but all the edges are positive. Okay, all the edges are positive half-lines. Okay. The other equation is the Korteweg-de-Vries equations. Okay, on general metrical graph, where A0 here is the area operator, which has action on every edges in this classical area operator. Okay. Okay. Some dynamical results have been obtained for the NLS. For example, the existing stability of standing waves, the Cauchy problem, and asymptotic behavior. Here I give some specific authors, but they are others. Okay, Adami et al., Abanika, and Bisiglia, and Indan Greco, Angulo Gorachopova, and Abdila. About dynamical problem for the KdV equation, we have a linear study about the ID equations and the existing stability stationary solutions, and about the Cauchy problems. Here I put a very recent results about this model by Cavalcante, Mugnolo, Noya, Seifter, and Angulo Cavalcante. Okay. After this long introduction, okay, let me talk about the main point of my lecture here. Here I will give some precise dynamical results in the case of the King-Soliton profiles for the Sine-Gordon model on a Y junction, or also known as Josephson-Johnson profile, okay, which appear in logic design circuits in computer. In other words, in computer and supercomputer device. Here I put a very innocent pictures about a Josephson line, which is a component of a superconductor's device. Okay, I put here three reference where you can see mm, the very important situation, okay, where the Sine-Gordon equation appear for describe very nonlinear waves and networks, okay? Okay, so let me start my study. More exactly, I will interesting here in this specific vectoral Sine-Gordon, okay? Puts on every edge on a Y junction, okay? Here, the constant Cj are real constants, and we note that the linear part of these systems can you write in this vectoral form, okay? I will use, okay, this expression on every edge, okay, for starting my study about the Sine-Gordon on a Y junction. Our first step will be a study, okay, what happened with the linear part of the Sine-Gordon equation on all the Y junctions. So it's possible to write this model in this vectoral form, where J is a matrix of order 6 with I3 is identical matrix of order 3. E represent a diagonal operator where F being this diagonal Schrödinger operator. Okay, and our first questions is to determine when this operator, okay, Ji, okay, Je is the infinitesimal generator of a C0 semigroove. Okay, from our experience of the semigroup theory, we know, okay, that a good star is considered F to be a self-adjoint operator, okay? Here, in my lecture, I will consider the case where the domain of this matrix Schrödinger operator is given by this delta domain, okay? Which is the delta integration case. Okay, for this domain, we obtain, in fact, that our operator A, okay, is in fact an infinitesimal generator of a C0 groove with this domain, the delta integration time EY, where EY are the easy space in H1 where we have the condition, the continuity in the origin, okay? Okay, by using the spectral information about the operator A, okay, operator A or G, okay, it's possible via the classical theory of semigroove to obtain this expression for the semigroove. Here, R lambda A represent exactly the resultant of the operator A, okay? By using this existence of a semigroove, okay, we can obtain the following local well-positiveness results for the Sine-Gordon equation on a Y junction, okay? Here we obtain that the Cauchy problem is well-positive in the space EY, okay, times L2. Moreover, it's possible to show that the mapping data solutions is a list of class C2, and for any positive time, the evolutions, okay, for the second component of the solutions belong to the space of elements of the space of the L2, which are continuous in zero. Yeah? Okay, the proof of this theorem follows from the Banach fixed point theorem if from the very important property of the semigroove that's left invariance this subspace. Okay, about the C2 flu property, the proof is based in the implicit function theorem. Okay. Now I will study about the dynamic of stationary solutions for the sine Gordon. Okay. Here I will consider. Okay. Here I will consider stationary solutions for this model on every edge of the Y junctions. I will consider that U has this profile independent of time, and B we will see. Okay, so every component of phi will satisfy these very known equations. Okay, so-called the King equations for the sine Gordon. Okay, well, from our information about the sine Gordon equation on the line, it's well known that these equations have these explicit solutions, okay, modulo translations. Okay, here the sign plus represent the very classic King solutions, okay, and the minus signs will represent in red here the anti-King solutions. Okay, with that information, and by giving that the condition that every component here initially from this formula, we obtain that every component phi of the stationary solutions has these King-Solton profiles, okay, with a specific translation. This chief A will depend of our conditions in the infinity, okay, and other or possible other conditions determining on the vertex of the graph. Okay, here I will consider the case where our stationary solutions belongs to this delta domain. Okay, this first condition, continuity in zero, will imply immediately, okay, that our chief A1, A2, and A3 need to satisfy these conditions. Okay. Now, by using these Kirchhoff conditions, we obtain immediately that the chief A1 satisfies this equation. Here is immediately that the constant Z, okay, the constant Z need to be negative. Moreover, by using the asymptotic property of this function f, we obtain that our constant Z, okay, need to belong to this interval. In other words, if you looking for by a profile, a stationary profile in the delta domain, you need to give some restriction about this parameter Z. Okay, now let me show some pictures. Here we obtain for Z in this interval a tail profile. solution of our stationary solutions. Here is very important to note that the range of our profile is smaller than pi, okay? The other one is the case of a bound tail profile for z in this specific interval. And here, okay, the value of the profiles in 0 is bigger than pi, okay? And for the specific case of z with this value, we obtain that all our translations or shifts j are exactly 1, okay? And so we will obtain a smooth tail profile. Okay, the following question here is to determine when or which are the stability properties of this stationary profile, tails and bound by the sine-Gordon fluid on an epsilon junction. Okay, so my first answer about this is that they are linearly unstable. Okay, so in the following, I will establish a linear instability criterion which will justify my statement. Okay, we start by writing our sine-Gordon equation in this vectorial form, obviously, with J in this form, with the matrix operators, okay, and F in the nonlinear part. Now, I will suppose that this operator, okay, GI, is the infinitesimal generator of a C0 group, okay? And I will suppose that we have a stationary solutions for the sine-Gordon in this domain and satisfies a king equation. Now I will suppose that if W satisfies formally the sine-Gordon equation, I will define this new variable B, and so we obtain, okay, the classical linearized system around the profile phi. Okay, for this model, okay, for this linearized system, we obtain that J is given by this matrix, and E is exactly this operator, where L is a diagonal operator of Schrödinger type, okay, given by this new potential, okay. Now, from this decomposition, we obtain immediately that this operator is also the generator of a C0 group. Okay. Now, the question here is to give, okay? The question is, the following analysis is to give sufficient conditions for the trivial solution, okay, V equals 0, for this linear fluid to be unstable, okay? So, I am interested, okay, in to obtain specific solutions with this profile, so-called growing mood solutions, where the profile psi will satisfy this high-value problem with a lambda having a real positive value. Okay? Okay. So let me give this following definition. We say that the stationary vector solutions is spectrally stable for the model sine-Gordon if the spectrum, okay, defined in this form, satisfies that is contained in the imaginary axis. Otherwise, we say that stationary solutions is spectrally stable. I recall the spectrum is divided in two parts, disjoint. The point spectrum, which are the eigenvalues, isolated eigenvalues, and the essential spectrum. Okay, here I will consider the case in our theory where J is a skew symmetric operator, E is a self-adjoint. So it's not difficult to show that the point spectrum is symmetric with respect to both the real and imaginary axis if the essential spectrum is contained in the imaginary axis. So we can say that stationary profile will be spectral stable if the point spectrum is contained in the imaginary axis, and it will be spectral unstable if the point spectrum contains a point with real part. That is the point that we are interested in here. Now I will establish a general linear instability criterion. Okay, here is, okay, for this abstract eigenvalue problem on a specific Hilbert space. Okay, suppose the following assumptions. J is a skew symmetric operator, E is a self-adjoint, J is a generator of Cicero semigroup, and suppose that E is invertible with a Morse indices equal 1, and the spectrum is decomposed exactly in that form. We have exactly one negative eigenvaluate, and the remain of the spectrum is contained here. Okay? With these assumptions, here I will establish from one result from Angulo Cavalcante 2020, we establish that with these assumptions, we obtain, in fact, that our operator has a real positive and a real negative eigenvalue. So this theorem gives solutions to our problem, our eigenvalue problem. Okay, let me apply, okay, exactly this criterion in the case of the king soliton profiles. Okay. Oh, let me talk about the proof of this criterion. Okay. The proof is not immediately, but here we use the theory of semigroup as on a specific Kanusinski theorem on closed convex cone, and naturally the spectral theorem for self-adjoint operator. Okay. Well, so our first application. Okay. This was a result in collaboration with Ramon Plaza in 2020, okay? And here we obtain that, in fact, our king soliton profile with a delta iteration in the vertex are spectrally unstable, okay? So from our comments, our established theory, our analysis is reduced to study spectral properties for this Schrödinger operator with this delta iteration. Okay, we obtain immediately from the Wells essential theorem that the essential spectrum is given exactly by this interval. Moreover, by using classical Sturleville theory in half lines, we can obtain that the kernel of the operator is trivial, okay? And so we obtain from this result about the essential spectrum that our operator is in fact invertible for every constant z. Okay, now about the Morse index of L on this delta iteration. Here we need to divide the proof in two parts, depend of the parameter z. For z, in this case, okay, the tail and a small tail profile, we can prove that the Morse index is exactly 1. The proof is based in the extension theory of symmetric operator, and I will give some outline of the proof. The first the first statement is that our family of operator L with this delta iteration represent all the self-adjoint operator of the closet of this closet symmetric operator, okay? And where M0 is given by these operators, the same action of the L, with a domain given by this condition to be zero and satisfies this Kirchhoff condition. With this information, it's not difficult to show that deficiency indices for the symmetric operator M0 is exactly 1. Now I will show that this operator is non-negative. Okay, for that, if I define Lj, this joint operator on each edge of the Y junction, and by using that this profile satisfies the King equation, we obtain that the action of Lj on every function is given exactly by this formula. This formula is well defined because our profile never has the derivative never vanished. Okay, well, so if we calculate the quadratic form associated to the operator M0, we obtain exactly this expression. This is positive, but we have two remainders here. But since our profile psi or the components, in other words, belong to the domain of the symmetric operator M0, we obtain that 0 is 0. So all this yellow remainder is exactly 0. In other words, M0 is not negative. Why this information? Because there is some specific proposition or result of the station theory. We say that if you have a lower semi-bonded symmetric operators, okay, okay, with a finite deficiency, yes?
5 minutes.
Okay, okay, thank you, okay. With a finite deficiency indices equal, okay, then we obtain that for every self-adjoint station, we have that the spectrum in this interval is discrete and consists of a mass k eigenvalues content multiplicity. If we apply this result in the case of the operator M0, okay, we obtain that M is exactly 0. So the spectrum of every self-adjoint station, in particular L, will have a Morse index smaller or equal to 1, because in this case M is 0. Okay? So in conclusion, we obtain some estimate for our Morse index. Now, the idea is to show that the Morse is bigger or equal to 1. For that, okay, I use that the quadratic form associated to L, which is given by this formula, is exactly negative for these values. Here we use exactly this information about the tail profiles and this very classical information. So from the minimax principle, we arrive that we obtain, in this case, for these values of psi, the Morse index is equal to 1. Okay. In the other case, the proof is not immediately. In the case of bound tail profile, here again we obtain the Morse index 1, but here we will use the analytical perturbation theory based in a continuation argument based on the risk projection, and by using that for this specific value of Z, we obtain this spectral information. So here I finish the proof about the stability, spectral stability of our Okay, let me establish our nonlinear instability result. In fact, our king soliton profiles will be nonlinear unstable. Okay, the proof is not immediately, but the main point for the proof is based in that the fluid data solutions for the Sine Gordon is C2 class, and the information about the linear unstable. Okay, let me finish my my lecture by put some possible future studies. It's very interesting in superconductors to study the existing stability static solution for the Sine Gordon on metric graph. So I will leave here this point. Now, by finishing, I want to give some relevant reference in my lectures. Okay, the papers with Cavalcante and Ramon Plaza. Okay, and these books. Okay, thanks.
We would like to thanks again Jaime for the very nice talk and for accepting our invitation. Thank you, Jaime.
Okay, Carlos, thank you very much for the invitation. Okay, thank you.